Hi everybody, so we're in section 4.2. We're going to be looking here at the mean value theorem. So one of the big theorems in calculus. In order to understand the mean value theorem, first we need to look at a special case, and this is Rolle's theorem. So Rolle's theorem says, let f be a function that satisfies the following three hypotheses. So we have three conditions that have to be satisfied. We have f is continuous on the closed interval from a to b. It is differentiable on the open interval from a to b, and f of a equals f of b. If we satisfy these three conditions, Rolle's theorem states there is a number c on the open interval where the derivative is equal to 0. Okay? There is some value on this interval ab such that the derivative is equal to 0. So here we have just an example graph. So this is saying that if we have f of a and f of b are equal to each other, the function is continuous on the closed interval, it's differentiable, or the derivative exists, on the open interval, then there must be at least one point where the derivative equals 0. And on this function that would be like right here, right? If we look at a tangent line, that's horizontal. This one also has a second one, right? You can have more than one, that's fine. We have a horizontal tangent there. So this would be our c value. We'll go ahead and call them two different things. So I'll call them c1 and c2. So these would be points that have a derivative of 0 or a slope of 0, and those are guaranteed by Rolle's theorem. So for this first example here, we have a little bit of a proof here. Show that the equation x cubed plus x minus 1 has exactly one real root. Now, we've done questions like this before where we showed that an equation had at least one real root on an interval, and that was by using the intermediate value theorem, right, the IVT. So let's just look at a couple points here. So let's let f of x be the function. So f of x equals x cubed plus x minus 1. Then if we look at a couple sample points here, let's look at 0. F of 0, that's 0 cubed plus 0 minus 1, that's negative 1. And f of 1, that's 1 cubed plus 1 is 2 minus 1 is positive 1. Now, since we know that f of 0 is less than 0 and f of 1 is bigger than 0, so f of 0 is less than 0, less than 0, which is less than f of 1. And the function is continuous. And we know the function is continuous since it's a polynomial. Polynomials are continuous everywhere. So since the function is continuous, and one of the values is less than 0 and one of the values is greater than 0, the intermediate value theorem, so the IVT, states that there must exist at least one point, call it C, one point C, where f of c equals 0. So in other words, there must exist at least one real root on this interval. Now, that gets us part of the way there. Okay, we know that there must be at least one root. The real question is now, how do we show that there is exactly one root? Okay? So in order to do this, we're going to be doing something called a proof by contradiction. So a proof by contradiction, A proof by contradiction, we assume the opposite of what we're trying to prove. So we're trying to assume basically a false statement. And then by the end of the proof, we come up with some sort of reasoning or actual proof that the statement we started with is false. Therefore, the opposite must be true. Okay? So if we were to show, in this case, we're going to assume there are two roots. So we're going to assume that there are two roots, and at somewhere along the line here, we're going to come up with some sort of contradiction, some sort of false statement that tells us conclusively there cannot be two roots. There must be only exactly one. So, since we're assuming two roots, call them f of a and f of b. Then we know f of a and f of b are both equal to 0. Right? That's what makes them a root. So f of a equals f of b, which equals 0. Now, for this function in question, we're looking at a polynomial, okay, x cubed plus x minus 1. Polynomials are continuous everywhere. They're also differentiable everywhere. So what we just established, so since f is a polynomial, it must be continuous on the closed interval from a to b, and differentiable on the open interval from a to b, and f of a equals f of b. Right? That's what we just established right now. F of a equals f of b because they're both 0. These three statements, so it's continuous on the closed interval, it is differentiable on the open interval, and f of a equals f of b. By these three conditions, we see that we can use Rolle's theorem, right? Because those are our three conditions here. So Rolle's theorem says there must be some number on this interval where the derivative equals 0. Okay, so we can say thus, Rolle's theorem states there is a value c. There's a value c on the interval AB such that f prime of c equals 0. So now let's look at the derivative of this function. Okay, so we're going to use the power rule here. So we have x cubed plus x minus 1. So f prime of x is 3x squared plus 1 plus 0, minus 0. Okay. Now, one interesting thing about this function, and this is where this whole argument is going to fall upon, is the fact that Rolle's theorem guarantees us that since these three conditions were met, there must be some value where the derivative equals 0. However, notice something about this derivative function that makes it a little different, a little unique, is that no matter what value I put in here for x, whether it be positive, negative, or 0, I'm always going to make it positive and then add 1 to it. This value must always be at least 1. No matter what the x value is, this function, this derivative, will always be at least 1, which means it can never be equal to 0. So f prime can never be 0. That's a contradiction. Because again, Rolle's theorem guaranteed us there must have been at least one place on this interval where the derivative was 0, but we just showed that's not possible. So, since we derived a contradiction, that means the thing that we assumed at the very beginning must have been false. So, thus, there cannot be two roots. Therefore, the function must have exactly one real root. And that's it. Okay, so again, we use the IVT, the intermediate value theorem, to show that there was at least one real root. And then we used Rolle's theorem and then a contradiction. We assumed to the contrary. We assumed, well, what if it had 2? What would happen? Well, we would receive a false statement. That cannot happen, so there must be only exactly one real root. This leads us to the big theorem for the day. That's the mean value theorem. The mean value theorem is similar to Rolle's theorem. In fact, Rolle's theorem is actually a special case of the mean value theorem. So the mean value theorem states if f is a function that is continuous on the closed interval ab and differentiable on the open interval from a to b, there must be some number c in the open interval such that f prime of c equals f of b minus f of a over b minus a. And you can also rewrite it using this way also. But basically what this is saying is the instantaneous rate of change at c is equal to the average rate of change over the entire interval. Okay, so the mean value theorem states if we have continuity and differentiability, there must be some number on AB where the instantaneous rate of change is equal to the average rate of change. Okay. So graphically, the average rate of change would be connecting A to B. So we're looking at something like this. Okay, so the slope of that line would be f of b minus f of a over b minus a. And there must be at least one point, and in this case there will be a couple, where the slope of the tangent, so maybe right about here, and right about here, the slope of that tangent is parallel to the average rate of change. So the slopes here and here are equal to the slope of that average rate of change. Okay, so this would be, right, C, we could call it C1 and C2 again, right, but that would be f prime at C1 and f prime of C2. Okay. So let's look at an example. We have f of x equals x cubed minus x on the interval from 0 to 2. Verify that f satisfies the hypotheses of the mean value theorem, and then find the number c that satisfies the conclusion. So the hypotheses of the mean value theorem are the continuity and the differentiability. So we can say, regarding continuity, this is a polynomial. So we can say, since f is a polynomial, it is continuous on 0, 2. Okay. Then, to talk about differentiability, we actually need to look at the derivative and see where it exists. So let's get the derivative. So f prime of x, that is 3x squared minus 1. Now this derivative, f prime, so f prime, is also a polynomial. So since the derivative is a polynomial, that means it must exist everywhere. Thus, f is differentiable on the on the open interval from 0 to 2. So the hypotheses are met. So it's continuous on the closed interval, differentiable on the open interval. So now we need to find the value of c that satisfies the conclusion. So f prime of c must equal f of b minus f of a over b minus a. So f prime of c, well, that's just the derivative up here, but with c instead of x. So that's just a notational thing. So that's just 3c squared minus 1 equals a and b. In this case, we're going from 0 to 2. So this is f of 2 minus f of 0 over 2 minus 0. F of 2 is 2 squared is 4 times 3 is 12 minus 1 is 11. Oh, I'm sorry. No, that's the derivative. So the original function, we're looking at 2 cubed minus 2. So that's 8 minus 2, which is 6. That's 6 minus 0 over 2 minus 0. And we still have the 3c squared minus 1 on this side. So now we just solve for c. So that's 3c squared minus 1 equals 3. 3c squared equals 4. C squared equals 4/3. So c equals plus or minus the square root of 4/3. We can go ahead and reject the negative case because it has to be the interval from 0 to 2. Okay, so we get c equals, go ahead and take the root of the 4, so 2 over root 3. And that would be the c value, where the slope of the tangent is equal to the average rate of change. Okay, so if we look at this on the graph, right, our average rate of change from 0 to 2, that's right here. That's our average rate of change. And then if we found the point at 2 over root 3, which is going to be somewhere in here, you would get a tangent that is parallel to that average rate of change. Okay. So that's what's happening here in this mean value theorem example. One application of the mean value theorem is, of course, with motion. Particularly when we talk about velocity. If an object moves in a straight line, then the average velocity must be equal at some point to the instantaneous velocity on this interval. So, for example, if a car traveled 130 miles in 2 hours, the average speed is 65 miles an hour. That means that at some point during this drive, they must have been going 65 miles an hour at least once. Right? They might have been going, 25 miles an hour stuck in traffic, and then they go 85 miles an hour for most of the rest of the way when there's no traffic, but at some point, they had to have hit 65 miles an hour. Right? And if you think about it, you can't get up past 65 without actually hitting 65, right, at some point. So that's what the mean value theorem tells us in a more practical setting. Now, the mean value theorem can actually provide us with some very fundamental basis of proof. So we can use it to prove all sorts of calculus results. We're going to look at one of them right here. So this says if f prime of x equals 0 for all x in an interval, then f is constant on the interval. Okay? So we're going to assume that f prime of x equals 0 for all x in the interval AB. So what we're going to do is we're going to pick a couple new values. So we're going to pick two values I'm going to call x1 and x2. So we're going to let x1 and x2 be arbitrary values on the interval AB. And when I say arbitrary, I just mean they can be anything. So x1 and x2 are just going to be any two values that we want on the interval AB. And we're going to assume x1 is less than x2. We say without loss of generality. So one of them has to be smaller than the other, so we'll just let x1 be the smaller one. That's kind of a minor point. So we know, since f prime is 0 for all points, right, f prime of x1 must be 0, and so is f prime of x2. Okay, so the derivative at both of these points must be 0. Okay. So now, if we're looking at utilizing the mean value theorem, when you start thinking about this in the context of instantaneous rates of change versus average rates of change. Okay. So, if we have for the interval x1 to x2, we know f is continuous and differentiable. The reason we know this is because of this initial statement. So we are assuming that f prime of x equals 0 for all x. Well, if f prime of x equals 0, that means that the original function had to exist at all those points, so it's continuous, and the derivative must exist at all those points because it's 0. So it's continuous and differentiable. Thus, since it meets those two conditions, the mean value theorem states there is some value in the interval from x1 to x2 where f prime of c equals f of x2 minus f of x1 over x2 minus x1. Okay. Now, this value, f prime of c, we know that the derivative at all points must be 0. Okay, we know the derivative at all points must be 0. And from this statement up here, if I just subtract subtract x1 over, I get x2 minus x1. I know that that's positive. It's not 0, right? So this is good. That means I'm not dividing by 0 here, because that's always a concern we have when we're dealing with fractions like this. I'm going to multiply this across, but anything times 0 is just 0. So what this gives us is f of x2 minus f of x1 equals 0. So f of x2 equals f of x1 for all x1 and x2 on the interval from a to b. So what did we just show? We just showed that if we know the function is continuous and differentiable, that means that for any 2 points that we pick on the interval a, b, the output of one must be equal to the output of the other. Let me say that again. For any 2 points on the interval, the output of the first one must be equal to the output of the second one. So since the outputs must be equal for all points, that's what we mean when we say a constant function. So since all outputs are equal, f is constant on AB. All right. So we use the mean value theorem to prove our definition of a constant function. Now, this last one down here, this corollary 7 down here, this one is very similar to the one we just did, so we're not going to go through the whole thing together, but what we would do to set this up is we would let h of x equal f of x minus g of x. Once you set up h of x, we prove similarly to the previous for h. So we basically do the same proof that we just did, but do that one on h. Then it gives us our result for f minus g. Okay, so we basically do the same thing we just did, but do it for the difference instead of just a single term, and then it gives us the same result, that we have a constant function on an interval. All right, and that is our mean value theorem. So that's it for this section. So I'll get this one posted up for you guys as soon as possible, and you can get started on it. So good luck, and let me know as always if you have any questions.